I'm Joseph Guidry. I'm a second-year PhD student at Boston University working in the White Dwarf group there with J.J. Hermes. And I'm excited to talk to you about sort of these similar systems, but now we're working edge-on. So these debris disks, like Nicola showed, which may have two different disks going on or something, are now inclined along the line of sight. And so I want to talk to you about these systems that show transits from this planetary debris, and especially about measuring their orbital periods, why that's so important, and how it allows us to place them in the broader context of these roadmaps towards pollution that Mark showed earlier this morning. And so it begins with this tidal disruption model. And so if we do a quick little recap, I love this, this cartoon from Eric Dennehy's PhD dissertation. We know we have this surviving population of planets and a reservoir of smaller minor planets like asteroids. And the instabilities and chaos from post-main sequence evolution, they're flung all around everywhere. Some of them are launched onto these star-grazing orbits. This is phase 2, where if they get close enough within this tidal disruption radius, which is nominally about a solar radius, or around 4 hours for a circular orbit, they will be subsequently tidally disrupted by the white dwarf and eventually fill out this disk, this accretion disk, which eventually pollutes the white dwarf photosphere. And so we think this is a good model. It explains the pollution we see. But again, I like to think about it and look for the ones that are inclined along the line of sight. And we finally got evidence for this with WD 1145 in 2015, thanks to K2. And it showed these irregular transits that repeated every 4.5 hours. So right near that tidal disruption radius. And so we can assume that it's like a disintegrating asteroid-like body that are showing these transits. And I like this light curve which was obtained in follow-up from a study that Boris led, because I think it highlights the sort of irregularity pretty well. You can see these red fits, which if I interpret it correctly, show what a solid body would look like that produce the same depth. But this was just the first case. Now we're up to a zoo of them. We think we have nearly 20 now. And so here's just a sample of them. I think I'm showing 9 different systems here. And you can see the contrast in the sort of timescales we're working with here. So on the left, I'm showing Zwicky transient facility light curves, which now have a baseline that it spans well over 1,000 days. And so there you can see transit-like dips that occur on the order of months and last weeks. And this is contrasted on the right by follow-up photometry we've obtained, which are showing variations on the order of hours. But importantly, even though we might be up to 20, and there's 9 in the zoo I'm showing here, only 4 of these systems have measured and published orbital periods. Still, we see a pretty tremendous dichotomy. On the left, we have one system which shows a period of around 110 days. And on the right, we have 3 systems which have periods ranging from 4.5 to 25 hours. And this is exciting because it might be giving us a window into different stages of evolution of the debris' tidal disruption. And so what I mean by that is maybe these longer period systems are probing phase 2, whereas the shorter period are probing phase 3. And if we can build up a census of these orbital periods in these systems, we might be able to place them into the context of this map and begin to answer questions like, oh, well, maybe we start to see differences, fundamental differences in the properties of these systems as a function of orbital period. What I mean by that is maybe the longer period systems beyond their light curve look very different from the shorter period ones. And that might inform us about the role of other processes like collisions or rotational fission in the evolution of the debris. And so that's why I think it's really important to measure these orbital periods and grow it from 4 to the 20 or so that we have. And so I want to begin to talk about how we can do that some, what we've done, and kind of how we're able to measure some of the orbital periods already. And I'm going to do that by using the most recently published orbital period, WD 1054 - 226. And so Jay Farihi led the effort of this, and it shows this remarkable 25-hour repeating pattern. I've drawn some arrows here to kind of anchor you, but I think the pattern is compelling enough that you don't need them. It's sort of always in transit, this system, which is so interesting about it. And so we got this 25-hour number largely from Fourier analysis. So here I'm showing periodograms, 2 periodograms. The top is from 3 consecutive nights of ground-based follow-up using ultracam, which is a high-speed photometer, similar to the light curves I just showed on the previous slide. And on the bottom, I'm showing the test light curve transformed into Fourier space, one of the test light curves. And so here we were able to, pull out that 25-hour fundamental with high precision, really thanks to tests. But we don't always have tests, which is unfortunate. So a lot of the times, when we're trying to establish the candidacy of these systems, we have to use a lot of ground-based follow-up. And frequently, they're pretty faint. So we kind of get some noisy light curves like this that are hard to work with. And so in this candidate, if you computed the periodogram of it, you would see a strong signal at 2.6 hours. And actually folded all these light curves here on that period, but nothing really lines up too well. The laser pointer isn't really working, but you can see there's sort of like a dip there, and it doesn't really match up there. So I'm beginning to think that this might be like the rotation of the star, perhaps. And so this has been motivating me to look for alternative period finding tools, alternatives to Fourier techniques, to complement them and maybe extract all the information we can out of our ground-based follow-up like this that we might be missing. And so in Tübingen, I was team autocorrelation functions. I thought they were promising, but I landed on a new technique called phase dispersion minimization recently. And in chatting about this with JJ, he put this idea in my head that I've really liked, where sort of thinking about this technique as minimizing the path length and flux in the light curve whenever you fold over a given trial period. And so you're trying to minimize this theta metric here, where S squared is the weighted average of all these path lengths in all your bins, and it's weighted to the number of points in that bin. And it's all normalized to the path length of the original light curve. And so here you can see in this bottom light curve, the path length is shorter, so that would be the better period. And so what this looks like in practice, here I'm using this sort of sawtooth-like light curve, which is a white dwarf, which has a spot rotating in and out of the field of view. And I'm using Ruth Angus's Python package that implements this algorithm to do this. And you can see that right at about 0.7 hours, the dispersion is minimized. It sort of checks out if we eyeball the light curve. You can see at least one subharmonic, which Stellingworth says is kind of a sign that this is a real period. And so that's cool. But again, we care about transient debris systems. And one of the reasons I've gotten excited about this technique is it was designed specifically for non-sinusoidally varying and irregularly sampled light curves, which is just like the follow-up we collect of our transient debris systems. And so, well, let's see if it works. So I went in and looked and see if we could, verify it was working with the test light curve first. And so I saw like a signal at 25 hours. I saw some harmonics, subharmonics. So I was like, okay, we're on the right track. But again, I really want to see if this works with our ground-based follow-up. And so here's an example of that. Again, you can see like a signal at around 25 hours. It's not centered, which is interesting. Instead of subharmonics, you're seeing harmonics. Other things that aren't harmonics of 25 hours. In 1054, we know there are independent drifting fragments of debris. So these are pieces of debris that are on different orbits from the fundamental 25-hour. In the case of this one, there's a 25.5-hour piece of rock or something that's orbiting the star. And so I've been wondering if some of these minima are other independent drifting fragments. So you can see there's some here, and there's especially one at around 15 hours. So I kind of looked at that to see what it would show. But curiously, a lot of the cycles in this light curve don't really overlap. So I've marked in red here the points where there is some overlap in phase, but everything else you can't really test. And so I think one of the problems that's in front of me and where I need to do my homework is finding out which of these minima are sort of real, or maybe accessible is the right word. Like, which of these periods do we actually have access to? And so this is all still quite exploratory and trying to figure out how I can best utilize this tool. But I still think it's very promising for these data, and I think it will allow us to measure more periods in this growing class. And hopefully we can see and populate the dichotomy a little more soon enough. So I look forward to some discussion about this and open the floor for that. Thank you.
Thank you. Questions? Oh, we have one in the back.
Thanks for the talk. So yeah, going back to the all those little peaks that you had in the so seeing those gaps between the light curves and that you don't have very well sampled phase, you can see similar features due to aliasing when you have like daily gaps in periodograms as well. Sorry. So I'm wondering if there's a way to maybe explore the effective gaps in your data using the test data as a way to kind of artificially introduce gaps, and whether that might be useful for understanding the behavior here.
Yeah, that's a good idea. I think that's worth doing. Because yeah, it has to be picking up something.
Oh, okay. Wait.
Hi. In this dichotomy idea that you have with the phase 2 and phase 3, do we also see any difference about other observables we have of the white dwarf between the systems? So am I right in saying that not all the long period ones show metapollutions or infrared excess, while the short 1145 definitely does?
Yeah, so I think 1145 is the only one that kind of shows all of the traditional signposts, like circumstellar gas absorption and infrared excess. 0328 shows what we think is circumstellar gas absorption, but none of these others show infrared excesses. They are all metal polluted. J0139 might be sort of transient in its, or variable at the very least, in its metal pollution. But so far, of these four, 1145 is the only one that kind of shows everything.
Thanks.
Yeah, I think you mentioned that the eccentricity for the longer period one here was a lot higher. So observationally, what indicates this higher eccentricity?
It's sort of a requirement of tidal disruption, or we think so, at the very least. So the debris has to come within the tidal disruption radius for it to be tidally disrupted. And if it's on a 110-day orbit, if that was circular, that would just be way far out. So we think it's probably the best idea is that it's sort of highly eccentric, and it's spending most of that 110 days out here and then passing in front of the star at Perry-Center.
If I can just ask a second question. So you were saying that the period is more than 100 days, but you didn't determine the period issue, or is the period still determined, and is it just more than 100 days?
It's determined. It's sort of an interesting system in that like, for a while around here, it was around 107 days, and I think one of these transits came early or late. So it's an interesting system in that it's not super exactly 107 days or 110 days, 104 days, but it's 100 something plus or minus a few days.
Yeah, it's just interesting that even 100 days is a lot less than what sort of the original orbit would be if it comes from a few AU, right? Which is the minimum distance that would not be engulfed by the star.
Yeah.
So even here we would be looking at a system that's already contracted quite significantly from the initial position.
Yeah, I see what you're saying.
Okay, then if I can ask quickly, how are you planning to convert your orbital periods in ages? Or, how can you use the orbital period to translate that into an age?
Yeah, I don't know if you can get a number yet, but it's mostly like a sort of qualitative way or a way of thinking about it. Like this might be more recently disrupted than this. I think that's all you can sort of confirm or
so you
conclude.
can just say something is older and something is younger, but not get absolute numbers.
I think so.
Okay. Any more questions? Okay. If not, thank you very much.
Thank you.